Okay, this little section here at the end is just a simple application of eigenvalue, eigenvectors to filter design. So suppose I have a linear time invariant filter that I need to design. Okay, so in other words, I need to define, it's going to be a finite impulse response filter, so I need to define the coefficients of this filter H. So I've got a signal that comes in F, and I've got noise that comes in nu. And suppose that that nu is white noise with variance sigma squared, and F is some zero mean random process. And what I'd like to do is pick H to maximize the signal to noise ratio. So if I know basically the size of the noise, and then I assume something. This is like, for example, a communication channel or something where you don't really know what's coming in, so we'll make assumptions that it's stationary, zero mean random process. How do I pick H to maximize the signal to noise ratio? In other words, I want this to come out of Y more than the noise. All right, so the signal, let's go ahead and stack this in terms of vectors. So we've got, if M is the length of the filter, then we can look at, the output. We just need to look at the past M inputs to the system. So T minus 1, T minus M minus 1. This is the last M inputs. And so the output is going to be H times F. And the output power, what's the power due to the signal F? So it's going to be the expected value of Y squared when there's no noise, so when we only have F. So this will be the expected, so the expected power, or the power of the output due to the signal, is going to be the expectation of Y of t squared. And so remember, power, well anyways, yeah, power, if we relate it to the output squared, then the output is going to be little h Hermitian times F squared. And so we have the expectation, this thing is a scalar, and when we square it, we just have, h Hermitian F, h Hermitian F, and then we have the expectation of that thing. And notice I can always write this guy as FH. I can write this guy here as F Hermitian H. And so when I do that, I get H Hermitian F, F Hermitian H. And the H's are not random. So the only thing that's random is the input. So I can write this as H Hermitian expected value of FF Hermitian times H. And then this guy, what is that? It's going to be essentially the covariance of the input signal, R. Okay, now let's look at the power due to the noise. So again, we look at the last M values of the noise, and the output due to the noise is going to be H times nu, and the average noise power in the same way is going to be, H Hermitian, and then expected value of nu H times nu Hermitian times H. And then we know that this guy has variance sigma squared. So in other words, I've kind of, this is going to be H Hermitian expected value of nu Hermitian times H, and this is sigma squared I, and so we get this value. So now if we look at the signal to noise ratio, it's going to be the power in the output due to the signal divided by the power in the output due to the noise. And when we plug in those previous equations, we get that, this shouldn't be in there, we get H Hermitian, or H Hermitian R H over H Hermitian here, And this is the Rayleigh coefficient. We talked a little bit about this at the end of the quadratic form discussion. So when is this guy maximized? It's maximized precisely when h is the largest eigenvector of R, and the maximum value is going to be equal to lambda 1. So the signal-to-noise ratio is going to be lambda 1 over sigma squared, where lambda 1 is the largest eigenvalue of the essentially the covariance of the signal. And how do we pick h? Well, we pick h to be q1, the largest eigenvector of R. So yeah, we can use eigenvalue and eigenvector equations to design these linear time invariant filters, FIR filters, that maximize the signal-to-noise ratio. Okay, and that's all there is to say about these eigenfilters.